We explored in our last thought primer the idea of truth functions, the idea that in a given compound proposition, the truth value of its main operator will be a function of its component parts. And what we worked on was representing compound propositions symbolically using operators so that we could then determine, based on the truth values of the component parts, what the truth value of the main operator would be. So we could take a sentence like the one on your screen here. When Tess comes to class, we're all happy. And when we're all happy, we like working on logic problems. And we can represent that statement symbolically by first identifying the simple statements that comprise the compound statement. And those statements here are Tess comes to class, we're all happy, and we like working on logic problems. And we assign each one of those statements a letter. Here I've assigned these statements T, H, and L. And now we can use our operators to symbolically represent this statement and determine the truth value of the main operator. So, when Tess comes to class, we're all happy. That sounds an awful lot like a conditional statement to me. Sort of sounds like if Tess comes to class, we're all happy. And we can represent that using our horseshoe. If Tess comes to class, then we're all happy. Second part of the statement says, when we're all happy, we like working on logic problems. Okay, another conditional statement, when we're all happy, we like working on logic problems. And we can see that these statements here are joined with the word and we can represent that with a dot. Now remember, the main operator of a given compound proposition is going to be the operator outside of parentheses and brackets other than tilde, unless tilde is the only operator outside of brackets. Now, we don't have any tildes here, but we do have three operators outside of brackets, and that's a no-no. So we're going to have to do some bundling up here. We're going to have to group up pairs of our statements. It seems like looking at this statement, it makes the most sense to group the statements this way. When Tess comes to class, we're all happy, and when we're happy, we like working on logic problems. Okay, so now what we can do is we can take that statement and we can identify the truth values of its component parts and then start calculating other truth values. So let's say we show up to class, we look around, and there's no Tess, okay? So the statement Tess comes to class is false today. But we also look around and it's like, wow, man, everybody's really happy today. That is true. And because this line here represents a single moment in time, if H is true there, H has got to be true there as well. And of course it's true that we like working on logic problems. So that's true. Now I can use my knowledge of operators to determine other truth values. I know that anytime the left-hand side of a horseshoe is false, that horseshoe is true. And I know that anytime both sides of a horseshoe are true, that horseshoe is true. And I can use the truth values now of these horseshoes here to determine the truth value of this dot. Okay? And that dot is the main operator. Okay? So that means that under these conditions, even when Tess isn't here, this statement is a true statement up here. Now, there's something interesting about this. What this statement says originally is when Tess comes to class, we're all happy, and when we're all happy, we like working on logic problems. And even though Tess isn't in class, it still seems to be the case that we're all happy and we're digging our logic problem work. How could that be? Well, maybe there's something else that's going on that day that made us happy. Maybe somebody brought chocolate cake to class. So even though Tess isn't here, we're really happy because of the chocolate cake. We'd also be happy if Tess was here because, as the statement says, when Tess comes to class, we're all happy. But even with Tess not being here, we might still be happy. And if we're happy, we're enjoying our logic problem work. So what this sort of reveals here is that Tess being in class is a sufficient but not a necessary condition for us being happy. All right? Now, the challenge for us here, though, is this, I don't know if any of these statements are true or false. Neither do you. You don't even know who Tess is, right? So we don't know whether any of these statements are true or false. And if we don't know if any of those statements are true or false, we don't know if any of the operators are true or false. And we're really just left with a big question, right? Somebody says to us, when Tess comes to class, we're all happy. And when we're happy, we like working on logic problems. And we don't know whether that statement is true or false. And we have no way of figuring out whether or not that statement is true or false. And that raises a question for us. Well, what would be the conditions under which this statement would be true and under which this statement would be false? And that's what we're going to focus on in this thought primer. We're going to focus on a concept called truth tables, and it's going to be some serious fun.